Yes, well, thank you very much for the introduction, and also thank you for giving me an opportunity to present a talk during such a wonderful workshop. So today I would like to present a work which is joint work with my advisor, Professor Bhutan from Purdue University, and it is on asymptotic optimality and minimal complexity of classification by random projection, where we quantify minimal complexity via the generalization error and explore the connection between the generalization error and the complexity of a method used to classify. Let me first introduce the method of classification by random projection. Assume that we have a binary classification problem of potentially very high dimensional data where the data come from the space RD, and we have large n amount of samples of the data. We propose to generate a small n number of vectors from the unit sphere in d dimensions independently and uniformly. Then project the data in the direction of each vector and classify the projected one-dimensional data, computing an error of classification for each direction. We choose the projection direction, the optimal projection direction, that results in the smallest classification error, and then we assign classes to the original points in high dimension using the classes from the classification in one dimension. I would like to mention that this process actually can be viewed as a one hidden layer neural network where the weights which lead to the hidden layer are random, and n is the depth of the hidden layer, and the activation function is a sign function. This method gives a hyperplane separation between data, and in case that we would like to explore more complex separation, we propose to use polynomial transformation of the original data of some degree k before projecting. That would extend our feature space into a slightly higher dimension. D plus k chooses k, and then we choose the random projection in that dimension. So we ask ourselves how accurate can such a simple classifier be? And in order to answer this question, we need to somehow establish some mathematical language for what happens when we do the classification. So when we choose the classifier, we choose from a family of functions, a hypothesis set, which is often parameterized. And this family is either explicit, we can consider all polynomials up to degree 3, for example, or it is implicit, for example, given by the architecture of a neural network. We choose one particular function out of our family so that the training error is minimized. And usually we do it by choosing the parameter, which is one that minimizes our training error on a particular data set, training data set. But our ultimate goal is actually to classify data which we had not seen before, and we would like to know if the error on the new data will be close to the error on the training data set. In order to answer that question, it is useful to have a bound on the population error. If we assume that our data are generated by probability distribution on some data space, then the population error is the error that the classifier would make if it had to classify every point in that data space. And it can be bound, the population error, with high probability, at least 1 minus delta, where delta is our tolerance level. It can be bound by the training error that we chose to be small during the training process, and some generalization term EF. And the generalization term EF actually depends, it's a function of the tolerance, the number of samples, and the complexity of our family of functions. That is why we connect the complexity of our method to the generalization error of our method. We connect it to this generalization term. The smaller the generalization term, the less complex the family of classifiers is. For example, if we consider a family that is finite, for example, we're just choosing between x and x2, so the magnitude of this family is just 2. We can create a bound for the generalization term in this way. So that would be square root of 1 over 2n logarithm of 2m over delta. This is good news because this term converges to 0 when the number of samples goes to infinity, which means that given enough training points, we can push the generalization term as low as we want. But the problem usually is that the set F is not finite. Even for a simple case of affine separation, affine function, the set of functions that we consider is not finite, it's infinite. So that is when the VC dimension comes in and helps us out. The VC dimension is built upon the idea that even if we have an infinite number of functions in our family, we still have only a finite output on a finite number of data points. For example, if we have n data points and we classify either class 0 or class 1, we can have up to 2 to the power of n, and we cannot have more. So the VC dimension gives an upper bound for these different options that our family can provide on a finite data set. And here we can see the bound that it gives that depends again on the sample size, and here it depends on the VC dimension. It also converges to 0 as n goes to infinity. So it also gives a guarantee that the learning will be successful given large enough sample size. What we do in our work is that we show a tighter bound for the algorithm, for the method of thresholding after random projection. We do not rely on the VC dimension. Instead, we compute how many different options our algorithm can produce on a finite set. They're called dichotomies. And we build our estimate on the fact that our family can be split into n independent sets, each one corresponding to a different projection. And each family does not give many options for classification on a finite data set because it's only classification in one dimension. In the next slide, I have a comparison between the estimate for the generalization term for random projection and for an estimate given by VC dimension. On the vertical line, we have the value for the generalization term. It's computed using number of samples of 10,000 and the tolerance level delta equal to 0.1. And on the horizontal line, we have values for different n, so number of projection, which varies in between 1 and 1,000. As you can see, the orange and the green line, which correspond to the VC dimension, are constant because they do not depend on the number of projections. But here we compare what happens to the estimate, to the generalization term when n grows. As we can see, it has a steep growth in the beginning, but it flattens out. And for n less than 1,000, we can see that there is a gap in between the estimate for the generalization term for the random projection and for the algorithm with VC dimension equal to 2, where I would like to mention that VC dimension equal to 2 corresponds to a very simple algorithm. For example, if you compare affine separation in dimension d equal to 1. Since our population error is bounded by the generalization term together with the training error. It wouldn't be enough if we could prove that the generalization term is small. We also need to prove that the training error will be small. That is why we concentrate on asymptotic optimality of the algorithm in our paper as the next step. So we approached this topic from two standpoints. First of all, we consider practical standpoint, and we proved that given a training data set, there exists a degree k such that as n converges to infinity, the training error of the method converges to 0 in probability. The convergence is in probability since our training error is a random variable that depends on the random projection direction that we choose for our algorithm. Afterwards, we consider theoretical standpoint when we assume that we have full knowledge of probability distributions. In this case, it's possible to consider bias error, which is the smallest population error any algorithm can achieve. And we can also consider reducible error, which is an additional error to bias error for an algorithm you would like to estimate. And we show that if bias decision rule, which actually leads to bias error, splits the support of the probability distribution into two measurable sets, then as k and n go to infinity, the reducible error of the method converges to 0 in probability. So the overall method error converges to bias error, to the optimal error in probability. So in the last slide, I would like to show a comparison with linear separation, comparison of the separation using random projections with linear separation when the dimension of the data is growing. So here we would like to consider a comparison with an algorithm that gives a linear separation of d-dimensional data, and we know that its VC dimension is equal to d plus 1. And for each d, we assume that k equal to 1 is enough to separate data successfully. And we compute the number of projections necessary to separate data well. The formula for this number is given in our work, and it is not very tight because it's used for the proof, but it is too conservative. But still, if we use this number of projections to estimate our generalization error, we can compare it to the generalization, the estimate for generalization term of the linear separation and see what happens. So if we take a look at the table, we see that even for d equal to 2, the estimate for the generalization term of random projection is less than the one for the VC dimension. And for d equal to 10, it's almost twice as small as the estimate for the generalization term for the which was built using VC dimension equal to d plus 1. This comparison brings a little bit of a thought that perhaps algorithms which have a large VC dimension have a better estimate of their generalization error if we considered somehow explicitly how many different options, how many different dichotomies can they produce on a finite data set. And that would perhaps explain some better generalization properties of algorithms with high VC dimension. Okay, so this is the end of my talk. Our work is pending on archive. If you would like to see it, I can send a manuscript via email, and I have some acknowledgements on the last slide as well. If you have any questions, please ask away.